in helium atom, we tried the first order perturbation theory. This week, the TA will do that 6-fold multiple integrals for you. So he will demonstrate how step-by-step elementary integration can take you to the final answer. We also tried the variational method, again, the same 6-dimensional multiple integral. And then we see that there is an effect of screening coming in. So when we inspect what we have in the calculation for helium atom ground state, we start to see that we can indeed mimic the effect of one electron on the other by a averaged E&M-like electromagnetic potential energy function. So, and that leads us to a very important idea about the Hartree approximation. So that's where we were last time. So I will pick up from that point. I will go to an appendix that shows us a bit more about this self-consistent calculation. Then we come back to summarize the single electron approach to many electron atoms. So that is our goal today. So we try to look for a single electron treatment for multi-electron atoms. So that is the aim, okay? So let me pick up where we were. So last time we did a first order perturbation calculation for helium atom ground state, pretending that each electron is in something called the 1s atomic state. Then we realized that in the calculation, we have a 6-variable integration. If we first group all the terms regarding one electron, we call it the second electron, say R2. It doesn't matter which one is the first, which one is the second. But if we group all the things about the R2 coordinates, this variable regarding it as a second electron, we realize that we can give this term a classical physics interpretation. So it is like the second electron is spreading itself out in some 1s state so that it is providing at the position of the first electron, R1 here, you see, okay, the electromagnetic potential energy. Thereby, this term highlighted here is like an additional potential energy function that the first electron feels, okay? So the picture is like the nucleus. There's one electron called number 1. Of course, it sees the nucleus. We know how to write down that Coulomb attraction. However, there's another electron wandering around. Now, we have a way to include the effect of this second electron by including this potential energy function in solving the first electron's atomic states. With this idea, this leads us to write down an effective single electron problem. It is like a single electron Schrödinger equation to solve for what is the helium 1s and its energy. The Hamiltonian looks rather simple, but there's much physics hidden behind it. This is the kinetic energy of one electron. One electron sees the nucleus, so the first two terms is ordinary and can be solved exactly. It's hydrogen-like. And this term is what we just discussed. it includes the effect of the other electron in the helium atom on the one that we focus on. So it is in some unknown state to be solved, okay? And that leads us to the self-consistent idea. We want to solve this, however, this potential energy term also needs the solution. So we have to solve these equations in a punchline way, self-consistently, okay? That asks for self-consistency. In Cantonese is, in 普通话 is 记差, in Cantonese is 几合, I don't know, okay? Is what you guess as the input should come out as the output. That is the whole idea, okay? So let me pick it up from there, and then I will go to the appendix to tell you a little bit more about this self-consistent method. It is the most popular method in handling atom problem, solid state problems, and also molecular problems. So here I restate the helium problem, but in the simplified unit. It is in atomic units. The TA should have explained to you what is the atomic units last week, sample question 13 or something like that. Yeah. So if you missed that, then try to read the appendix A. This is appendix B, okay? Basically, the atomic units measure length in Bohr radius, measure energy in 2 times 13.6 eV. So everything is related to the hydrogen atom scale. Measure in the binding energy of hydrogen, only twice of it, 27 eV or so. Use that as a unit, and then Bohr radius as another unit. Mass in mass of electron, etc. Then the helium atom, Hamiltonian looks simpler, but it's the same thing, okay? You have a problem set to work this thing out, I think. So we discussed how to write down the effective single electron problem. This is the same equation that I just showed you 1 minute ago. So we start out from here, and then here, as last time we emphasized, there is a self-consistency problem. This is the output, what we want to solve from the equation. However, we also need this 1s state to construct part of the Hamiltonian. This is the effective electromagnetic interaction energy of the second electron on the first electron. So if we don't know the answer, we cannot construct this term to solve for the answer, okay? So there seems to be contradictory, but no, in physics and in mathematics, we just see the whole equation as one equation to solve for this unknown 1s state, meaning we make a guess, construct this part, solve for the output, compare the output with the input, adjust the input, and loop it again until what it comes out is what you put in. That is called self-consistent solution. So this is depicted here, okay? 1, you guess. 2nd, you evaluate that term. 3rd, you solve the Schrödinger-like equation. You have an output. You compare the output with input. You keep on looping this until you get a self-consistent solution, okay? And what I just introduce this self-consistent idea plus this form of self-consistent equation has a name. It was developed in the 1930s by Hartree and his father, so Hartree and Hartree. At that time, they don't have a powerful computer. Nonetheless, they can do some self-consistent calculation. I think some of them were done by hand. So just calculate it, okay? And then it was very successful. So it has permeated into molecular physics and also very popular in solid state physics. Of course, nowadays you can buy a program, buy a package to do Hartree and related thing called Hartree-Fock method using the package. You don't need to write it yourself. In quantum chemistry, again, you can buy a package, you can pull down a table, you want which one? Calcium. Then you can just click it and then the program will run out all the atomic orbitals for you. Nonetheless, it is good to know what is behind such methods. What I just told you fall into the name of Hartree approximation. It is also part of the idea behind something called the self-consistent field method. Self-consistent means the thing that I just told you, okay? The field means the wave function. The wave function generates the electromagnetic field in potential energy term, okay? So it is a general method. There is another similar method, including another name called Fock, that we will discuss a little bit of it later when we discuss helium atom excited state. Last time I mentioned briefly, when we treat the excited state, we have to deal with two different states, 1s, 2s. In such situation, in addition to the J integral, I introduce a J integral, we will see another funny integral called the K integral, which is called the exchange integral. And in that term, if we include that particular term into the single electron problem to solve for self-consistent atomic states, that is called the Hartree-Fock method. I have a little bit more to say, but not much, because that has to do with some more advanced level treatment. And if we do this Hartree calculation to the very best, meaning the same equation, one can solve it lousily, one can solve it rather accurately, okay? Now, for example, some people roughly just put in some 1s reasonably looking state with a parameter or two parameters, then insert it, construct it here, get the output, adjust the parameter only, and then put it back, and then they will get a self-consistent solution, okay? But some will use a more elaborate form of the input, and then the answer should be more accurate. Now, if one works out the best Hartree calculation, then the answer turns out to be the ground state energy is minus 2.86 Hartree. There is a so-called exact or accurate values to compare with. This is minus 2.9 Hartree. So you see, it is really not bad if you do this single electron approximation to a 2-electron atom problem. However, this is as good as one can do within this scheme. You cannot do better than that. You see that there is indeed remaining different, okay, that you cannot handle within this averaged field idea. We are treating the second electron as smearing out. This idea falls into a general idea called mean field theory. We are taking the mean effect of the second electron on one electron, okay? But in fact, the two electrons want to repel each other. This averaged idea cannot take 100% of the electron-electron repulsive effect into account. There's some remaining effect that one has to do something better, okay? To quantify how severe this remaining effect is, we define, if you have an actual value, that is the real value, we define the actual value minus the best you can do within Hartree or Hartree-Fock. That difference, the one that you cannot account for by self-consistent calculation, we call it the correlation energy. If this is big, that means we need to go beyond this averaged field idea to handle this problem. And in recent years, there is a big research area in condensed matter physics called strongly correlated electron systems. This includes, for example, high temperature, high transition temperature, so-called high TC superconductors, quantum Hall effect systems, some of the magnetic systems. So for those systems, the interaction between electrons are so important or so strong that this kind of average field wave only form the first step of handling such a system. We need to do a little bit better, okay? So here I just want to introduce this term so that later on, when you have some opportunities to select some research topics, correlation, strongly correlation. What does it mean? It means this average way of handling electron-electron interaction is not sufficient in those systems. And then this is an optional page. I want to illustrate the Fock term, Hartree-Fock, that has to do with bigger atoms or excited states. So in bigger atoms, we need to handle electrons filling in not only 1s, but 1s, 2s, 2p. So we need some equations to solve for not only 1s, but 2s and 2p, for example. So if you think about it, when you have different states involved, you have to set up one equation for 1s, another equation for 2s, another equation for 2p. But in each of these equations, you will have the other electrons filling in these orbitals to provide the average potential energy function. When we do this, we will see suddenly we have some funny term in the effective Hamiltonian. I write down one here, okay? Now I write down one here just to illustrate that if you stare at this one long enough, you cannot find anything that you can interpret in the electromagnetic wave. For one thing, if you look at R2, this variable, in one term it is in 1s, in another term it's in 2s. if you look at the 2s state, in one term, it is another electron. In one term, it is the first electron, okay? So you look for all this phi, you will not see anything that is phi, okay? You don't see this, okay? But in interpreting quantum mechanics wave functions, we look for this phi square as the probability density. But in this term, we don't find it in anywhere, okay? So when we see this term in the one electron Schrödinger equation, then we call this term the exchange term. We will have a little bit more to say a bit later after we discuss how to write many electron wave function in a proper way. That is related to the Pauli exclusion principle. When we have two or more electrons, there is an additional rule. That additional rule will lead to this particular type of terms. We will see it again a bit later, okay? So I already discussed this looping self-consistent idea, so I don't need to discuss it here, okay? Now, another idea is that we must do one calculation, self-consistent thing for every atom. We cannot have one set of 1s, 2s, 2p, 3s states that is good for all atoms. It's not, free size, okay? You don't have one thing that is good for all atoms, because all atoms, you have to set up the self-consistent equation for that particular atom and solve for the atomic states. So when you were a high school student or year one student in chemistry course, you see this 1s, 2s, 2p, those energy level diagram. You thought that it is good for all atoms. Sorry, no. The alignment may be similar, but the energies are certainly different, okay? Even the alignment will be different when you go from light atoms to heavier atoms. So, key point, every atom is a different calculation, quantum mechanically. That is an important concept. But in doing so, we saved the idea of single electron atomic states. So somehow, even for helium, lithium, carbon, sodium, potassium, even to uranium, we can talk about 1s, 2s, 2p atomic states. But I hope that the next time when you see this, you have more ideas in your mind, because when we use it, actually, we have done some approximations in handling the electron-electron repulsive term in the full Hamiltonian of a multi-electron atom. So at this point, the remaining physics becomes, after you get these atomic states, the atomic physics people call it atomic orbitals, because you have this S like a ball, P like a thumb, an 8, the letter 8, something like that. That looks like some orbits, okay, but it's not its probability density distribution, okay. But nonetheless, this term is very popular. It refers to the wave functions 1s, 2s, 2p, etc. The remaining question becomes how to fill electrons into such atomic states. We will come to it a bit later, okay? that has to do with a general requirement. The wave function must change a sign from positive to negative or from negative to positive when you interchange the variables referring to two electrons. Number 1, number 7, change the coordinate, change the coordinate of two electrons. That wave function of the electron must change by a minus sign. That requirement turns out to be a more general statement of the Pauli exclusion principle that you learned in the past, and then we can understand the periodic table. So that is the remaining part of this chapter on atomic physics. Here, I just showed you how people, after doing this Hartree self-consistent calculation, get at all these atomic states for different atoms. I just want you to realize, if we are doing hydrogen, then we only get one S, okay? Because we are looking for the ground state here. And then for helium, we only get the 1s as well, because we put 2 electrons into the 1s, and we saw that equation. After solving this, this is the epsilon 1s. Lithium, we have 2 electrons in 1s, 1 electron in 2s, thereby we have a couple equation, 2 equations, self-consistent. Solving it, you get 2 energies, okay? So when you go down the periodic table, you see this is actually, first of all, the 1s is keep on changing from atom to atom, okay? As the atom is getting bigger, 1s drop, it deeper, because the nuclear charge is bigger, the attraction is stronger, okay? Near the closer to the nucleus. 1s is closest to the nucleus, okay? And then you also see the alignment. So this is deep sodium, 1s, then 2s is much smaller in energy. Of course, you can put a minus here. So minus 1s, 2s, okay? You see that is different by a lot. That's why you call this core state that will not be involved in chemistry much, okay? So, and then 2s, and then 2p, you start to see the difference. That's what you learn in high school. Not in hydrogen, but in other atoms, 2p is slightly higher than 2s, so this is what you see. And the 3s is really small in binding, thereby it can be detached, and sodium is a metal. You see? Although we are doing atomic physics, that is the beginning of the physics of all matters. We have conductor, we have insulator, we have semiconductor, we have superconductors. This is the beginning. You ought to understand atoms first, okay? So now I encourage you, when you review this part, try to look at some numbers in a row and then draw out the alignment, and you will see what you learned in the past, okay? How 3p is higher than 3s, and sometimes the 4s drop below the 3d, things like that, okay? So you have to look at the numbers. And that actually formed the basis for understanding the periodic table after we know how to fill in the electrons. Assuming that you have heard the Pauli exclusion principle, so if you have 11 electrons, sodium, you fill in the 1s2, 2s2, 2p6, that will be 10 electrons, then you fill the last one in 3s1, okay? So that is so-called electron configuration. Earlier, we also introduced the term symbol, thereby for any atoms, after you fill it in, you can look for the total S, total spin quantum number, total L, the total orbital angular momentum quantum number, and the total J, the total angular momentum, and put them in the corners, up corner, lower corner, then you have this term symbol for the ground state of an atom. Okay, so many things that we learn in hydrogen will be reused in all the atoms in the periodic table. Why do we discuss all this? Because it's very important in modern physics. We can hardly find something that is non-interacting. So when you have interacting system, we have to handle this interaction in some skillful way. And this self-consistent Hartree thing is the beginning of some very big ideas, some very difficult calculations in how to do electron-electron interaction. It is also the beginning of computational quantum chemistry and computational material science. In recent years, this computational material science is a very hot field, because if you ask the experimentalists to try this, try that, that will be very time consuming, and there are so many possibilities. However, if your program is written very nicely and include this electron-electron interaction effect skillfully, you can predict some properties before you ask the experimentalists to do something. That is computational material science. In our department, Professor Zhu Jinyi, okay, I think his group is doing something related to computational solid-state physics. There are packages that you can buy to do such calculation. A very popular one is called Gaussian, followed by the addition. It started from Gaussian 1993 or something, very early addition. I think nowadays the latest edition may be 2016, okay? So you can buy one of this, and then not very expensive. Then you have, the menu will give you many choices. Do you want to do it Hartree? Do you want to do it Hartree-Fock? How complicated this wave function you want to model it. But before you use it, it will be good you know what is it doing, okay? So with packages, the concept becomes more important than knowing how to write the program, okay? It is also the beginning of many-body physics, because even the method of Hartree and Hartree-Fock that we wrote down can be represented by a certain Feynman diagram. The correlation part that we cannot handle within self-consistent calculation can be handled by including some interaction represented by something called the Feynman diagrams that are not included in the mean field methods, okay? And the last point I want to do is that you have seen the periodic table many times, but I would like you to know, behind this periodic table and the things that you remember, okay? 1s2, 2s3, 2s2, 2p6, there is a lot of physics and a lot of quantum physics behind it. We still stick to quantum mechanics, but in a very skillful and in a very physical way, we handle some of the electron-electron interaction. And there are some big names. What I just discussed with you were awarded Nobel Prizes. Walter Kohn got the Nobel Prize chemistry, but he is a physicist, 100% physicist, for developing computational methods in chemistry. And then Slater, we will have a little bit more to do with his contribution a bit later. He's also a big name in this field. he established the MIT physics department as we know it now. And then he established the quantum theory of atoms, solids, and molecules. You can look up titles of his books under something like quantum theory of atoms, quantum theory of molecules. Okay, he wrote several books. And for those who want to read more, I give you a few very readable references for undergrads. So I will see if you have any questions. This appendix is something kind of extra, okay? I want you to get the idea. I don't need you to know how to do the calculation. The calculation, you can buy a program to do it. Any questions? If not at this time, then let me summarize this idea and then what it does to our understanding of atoms. So we discussed rather lengthily the idea of reducing many electron problem, turn the many electron problem to effective single electron problems. Okay? Hartree is an illustration of how complicated that method could be. Nonetheless, at the end, we do have this single electron effective Schrodinger equation. And we have seen equation of this form. We focus on one electron in some atomic state. We call it atomic orbitals, as mentioned. The electron has its own kinetic energy. It sees the nucleus, so no problem about the first two terms. And we saw all the other electrons is like contributing an effective potential energy to this particular electron we are solving. Okay, we have seen that explicitly in helium ground state. Now I want to generalize this idea to all other atoms. So we have seen this. If we group these two terms together, then all of a sudden, it looks like we have an atomic problem with one electron in an effective potential that combine, I should say effective potential energy function, that combines the nucleus effect and all the other electrons effect, okay? So with this, life becomes very easy. Suddenly, it goes back to something like what you did in the central force chapter in your QM1 last term, okay? You have that chapter, okay? I read the notes very nicely. So now, we also hope, at least we want it to be, that this is spherically symmetrical. It may not be exactly spherically symmetrical, but that is at least, we want it to be so that we can copy result, okay? So this is the idea. The problem becomes one electron in an effective potential that we, at least as a first approximation, being spherically symmetrical. So this picture means try to depict it, well, not very nicely. We focus on one electron. All the other electrons is providing this shaded average effect, that is this term, and the nucleus is providing this term. Together, they form an effective potential, okay? So, if we further assume or approximate this effective potential as spherically symmetric, That will be nice because immediately we know the atomic orbitals will come out to be this form. The YLM theta phi only depends on the spherically symmetrical potential. Okay, it is central field approximation, okay, or central force in classical mechanics. Only the radial part will depend on the exact form of this spherically symmetrical potential. The angular part is standard. It is always like this. In addition, we know that the energy on the right-hand side of the equation is related to N and L because this thing is not strictly Coulombic. If it were Coulombic, then it is epsilon only depend on N, as you see, as you have seen in the hydrogen atom problem. Okay. We also know more. YLM theta phi refers to orbital angular momentum magnitude square and the Z component. Okay, they are YLM theta phi is eigenstate of these two operators in addition to the Hamiltonian. So that is the nice thing. Okay, so let me summarize. Very complicated uranium atom. We pretend to focus on one electron, all the remaining thing providing an effective potential. We want it to be spherically symmetrical, okay? Therefore, we assume it to be. And then we have this, immediately we know this form of the wave function. We can talk about 1s, 2s, 2p, things like that. Okay? And then we have this energy dependence. Now, what if the effective potential is not quite spherically symmetrical? Of course, there will be a residual electrostatic term then, okay? That means you want it to be like that. Of course, the exact form is this electron-electron repulsion. So if you want this to be like that, of course, you can subtract it out. Okay, so if you stop here and ignore this term, this is what we just assumed. That is to say, if you want to do it more accurately, you can come back later and treat this remaining term as perturbation. Okay, that is another way to do it more accurately. But here, I will not worry about this residual electrostatic interaction. And then we just pretend that it can be modeled by a spherically symmetrical potential. So now let's look at, in a very physical way, what this effective potential energy function would look like. We have this idea about 1s, 2s, 2p states. So you can think about it as the following. V of R, if R is very far away from all the other electrons, so you have Z electrons to single out one. If the distance from the nucleus is far away, well, you know the ballpark angstrom, right? So if it is 2 angstrom from the nucleus, you already think that all the other electrons should be inner electrons. Okay, so in this way, when R is far away, it's like you have the nucleus and then you have all the other Z-1 electrons. Thereby, you expect what you see is not the total nuclear charge, but screened out by the other electrons. Therefore, you expect that far away from the nucleus, what you see as the effective potential is just one charge from the nucleus, okay? Because there is Z-1 electron charge neutralizing part of the, or screening out part of the nuclear charge. Therefore, you would expect a potential energy just like E square over R. And now, if the distance from the nucleus is close to the small, it is close to the nucleus, then you can think about all the other electrons are outside the location. So in E&M, you also know that a shell of a conductor, okay, so electrons there, okay, would have no effect on you, right? They all cancel out a spherical shell, for example, okay? Therefore, you will see all the nuclear charge. So with this idea, at least we know two limits. When it is very far away, you see only one E nuclear charge due to screening. When you are very close to the nucleus, you see the full nucleus. Therefore, you have a Z there, okay? So draw it out here. Very far away, you see -1 over R. Very close to the nucleus, you see minus, for example, 92 over R, okay? So this is going steeper than that one. Now, what happened in between, nobody knows. You have to do self-consistent a lot of things. But if we just by hand connect the two limits, immediately we see at least point number one, we can save the spherically symmetrical idea. Second, it is not strictly Coulomb, okay? And therefore, we can only say this about the atomic state, okay? And the energy will depend on N and L because it's not strictly Coulombic due to screening effect in many electron atoms, okay? So therefore, we save a lot of work because we have much knowledge about central force problems. The state will be like this. The energy will be depending on N and L. Therefore, all other atoms, 2p is expected to be slightly higher than 2s. They should be because the potential is not strictly Coulombic. And we also know that given L, there is an ML degeneracy, spherically, what do you call it? Spherical harmonics. And then there is still a spin degeneracy. Each state can take on spin up, down, okay? So all in all, for a state, P state, for example, there will be 6 states. D state, there will be 10 states, as you already know in hydrogen atom. Therefore, a way to label atomic orbitals is just what we discussed a few weeks ago. Principal quantum number N and L, so NL will give us 3D, for example. And then behind L, there's an ML. The electron is always spin half. There's a S equals half, always skipped. And then we have the up-down MS. So this is the full description of many electron atoms, atomic orbitals, okay? So all in all, it relies on single electron picture of many electron atoms. Therefore, you finally see the old picture that you saw before, okay? But let me remind you, each atom is a separate QM problem. Don't take one alignment and work for all atoms, okay? Practically, it is good to remember one pattern like this. okay? Because the alignment is more or less the same, but the numbers will be very different. So let me pause here for a break, and then I will come back here, and then we can look at the periodic table, things like that, okay? So break now.